Image enhancement is the process of applying the technique to facilitate the development of a solution to improve the visual interpretability of an image by increasing the apparent distinction between the features of the scene. For example, emphasize sharpen and smooth image features for display and analysis. This objective is to create new image from the original image in order to increase the amount of information that can be visually interpreted from the data. Enhancement operations are normally applied to image data after the appropriate restoration procedures have been performed. The image enhancement process has a different technique, including contrast manipulation, spatial filter manipulation, and multi-image manipulation. And now we will learn about grade level thresholding in contrast manipulation. Grade level thresholding is also called grade level transformation. Is the process of taking the original grade level values and changing them to improve image. This process related to improving the image contrast and brightness. Image contrast is a measure of distribution and range of grade levels, the difference between the brightness and darkest pixel values, and how the intermediate values are arranged. Many objects or image regions are characterized by constant reflective or light absorption of their surface. A brightness constant or threshold can be determined to segment objects and background. As can be seen, thresholding is a limited case of contrast stretching. It produces a two-level binary image. Some fairly simple yet powerful processing approaches can be formulated with grade level transformation because enhancement at any point in an image depends only on the grade level at that point. Techniques in this category often are referred to as point processing. The second contrast manipulation technique is contrast stretching. This technique is to expand the narrow range of brightness value of an input image over a wider range of grade values. Certain features may reflect more energy than others, and this results in good contrast within the image and features that are easy to distinguish. The contrast level between the features in an image is low when features reflect nearly the same level of energy. When image data are acquired, the detected energy does not necessarily fill the entire grade level range that the sensor is capable of. This can result in a large concentration of values in a small region of grade levels, producing an image with very little contrast among the features. As you can see in the figure, if TR has the form as shown in the figure below, the effect of applying the transformation to every pixel of F to generate the corresponding pixel in G would produce higher contrast than original image by darkening the levels below M in the original image, brightening the levels above M in the original image. So, contrast stretching is a simple image enhancement technique that improves the contrast in an image by stretching the range of intensity values it contains to span a desired range of values. Typically, it uses a linear function. Here is an example about contrast stretching before and after applying the technique. The left image is the original image and the right one is the stretched image. And you can see the histogram, different histogram a before and after technique. There's different contrast stretching technique, including linear stretch and non-linear stretch. Linear stretch is a radiometric enhancement technique that improves the contrast of an image for visual interpretation purposes. A linear stretch occurs when the gray level values of an image are uniformly stretched across a larger display range. Usually, the original minimum and maximum gray level values are set to the lowest and the highest gray level values in the display range, respectively. For example, if the maximum gray level value in the original image is 208 and the minimum gray level values was 68, the stretch value could be set at 255 and 0 respectively. About nonlinear, that is a radiometric enhancement technique that stretches the range of image brightness in a non-proportional manner. A nonlinear stretch expands one portion of the grayscale while compressing the other portion. And here is the formula of linear stretch, in which dn is the original digital number of pixels in input image, and min is the minimum value of input image, and max is the maximum value of input image. And here is some example of linear stretching. The left hand side is the image before, and the right hand side is the image after applied linear stretch. And so you can see the image is more clear than before. And now I would like to introduce another contrast stretching technique, histogram equalized stretch. In this technique, an image processing technique that displays the most frequently occurring image values. The examination of histogram is useful tools, as it contains information of grade level distribution that easy to see the modification that may improve. Normally, histogram equalized stretch focus on histogram shape and range. Histogram with a small split has low contrast. Histogram with a wide split has high contrast. Histogram cluster at the high end corresponds to a bright image. The brightest region of the image will be assigned a large range of digital number values so that radiometric details is enhanced. And in this figure, you can see the difference between the contrast stretch enhancement, the difference between histogram, no stretch, linear stretch. Normally, histogram equalization process consists of 4 steps. First, find the running sum of the histogram values. And the second, normalize the values from the step 1 by dividing by the total number of pixels. Third, multiply the values from the step 2 by the maximum gray level and round. And fourth, map the gray level values to the results. The other contrast manipulation technique is slicing technique. This technique is used to highlight a specific range of gray levels in a given image, in which the gray levels or you can understand the digital number distributed along the axis of an image histogram are divided into a series of analysis-specified intervals. And all digital numbers falling within a given interval are displayed as a single digital number in the output image. The process of converting the continuous return of an image into a series of density intervals or slices, each corresponding to a specific digital range. And here is an example about grade level slicing. It can be implemented in several ways, but the two basic themes are: one approach is to display a high value of all grade levels in the range of interest and a low level of all other grade levels. This transformation, shown in the figure, produces a binary image. And in B picture, the second approach, based on the transformation shown in figure B, brightens the desired range of grade levels but preserve grade levels unchanged. And the figure C shows a grayscale image, and the last one in D shows the result of using the transformation in figure 8. About bit plane slicing, pixels are digital numbers, each one composed of bits. For example, the intensity of each pixel in a 256 grayscale image is composed of 8 bits. Instead of highlighting grade level range, we could highlight the contribution made of each bit. This method is useful and used in image compression. Assuming that each pixel is presented by 8 bits, the image is composed of 8 1-bit planes, and plane 0 containing the lowest order bit of all pixels in the image, and plane 7 on the high order bits. Only the most significant bits contains the majority of visually significant data. The other bit planes constitute the most suitable detail. Separating a digital image into its bit planes is useful for analyzing the relative importance played by each bit of the image. It helps in determining the accuracy of the number of bits used to quantize each pixel. The second image enhancement technique I would like to introduce is about the spatial filtering. As you can know, the larger neighborhoods allow considerable more flexibility. And the general approach is to use a function of the values of f in a predefined neighborhood of x, y to determine the value of g at x, y. And one of the principal approaches in this formulation is based on the use of so-called masks, also referred to as filters. So a mask or filter is a small, let's say 3 multiple 3 2D array, such as the one shown in the figure, in which the values of the mask coefficients determine the nature of the process, such as image sharpening. Therefore, the enhancement techniques based on this type of approach often are referred to as mask processing or filtering. And the filters are commonly used for such things are angle enhancement, noise removal, and the smoothing of high frequency of data. The principle of the various filters is to modify the numerical value of each pixel as a function of the neighboring pixel values. For example, if the value of each pixel is replaced by the average of its value of those of its 8 neighbors, the image is smooth. That is to say, the finer detail disappears and the image appears furniture. For example, the filter value of the pixel located at E5 is equal 5.86 89 and could be round up to 6. There are different spatial filtering techniques, including the neighborhood, the image profiles, the numerical filters, in which there is low-pass filters and high-pass filters. The first spatial filtering technique is the neighborhood. In this technique, a resampling technique that calculates the brightness value of a pixel in a corrected image from the brightness value of the pixel nearest the location of the pixel in the input image. As can be seen in the example, the digital number value is 9, and then after application the neighborhood technique, the output digital number pixel has the value 12. There are two different spatial filter manipulation. First one is the high spatial frequency, which used to make the gross errors, in which the high frequency corresponds to image elements of smallest size. An error with a high spatial frequency will have rapid change in digital values with distance. For example, dense urban areas and street networks. And the second is low spatial frequency, which is used for smooth areas. The low frequency corresponds to image elements of relatively large size. An object with a low spatial frequency only changes slightly over many pixels and will have gradual transitions in digital values. For example, a lake or a smooth water surface. Low-pass filter is used to give image softer or special effect, or to mitigate noise effects. For spatial domain is by considering a pixel and its neighbors and eliminating any extreme values with median or mean filters. Infradomain is accomplished by some form of low-pass filtering. There are some of average filters. The coefficients are all positive. Some common spatial convolution masks, where first two are standard arithmetic mean filters, and last two are approximation to Gaussian filters. Low-pass filters are normally useful in smoothing an image and reduce salt and pepper noise from such image. Here is an examination of image after applying the low-pass filters. As can be seen, after applying low-pass filters, details are smooth and digital numbers are averaged after a low-pass filter is applied to an image. Detail is lost, but noisy image and speckle inside image are smoothed out. In high-pass filters, this technique is used for removing stripped noise of frequencies, for example, low energy, long short wavelengths. These methods use a high boost spatial filter, a tree multiple kernels with a value of 8 for center pixel and value of -1 for the exterior pixels. This mask is converged with the image and value determines the amount of low-frequency information retained in the resulting image. Value 8 high-pass filter output image will contain only the X. Larger value will retain more of ori image, less than 8 negative of ori. High boost mask can be extended with -1 and a corresponding increase in the value. Larger mask will emphasize the X more and help to mitigate the effects of any noise in the original image. And if we create n multi-n mask, value is n multi-n -1. And this technique can be used to enhance X between different frequencies as well as to sharpen an image. And here is an example about the image after applying the high-pass filter. In which image you can see that streets and highways and some streams and drifts are greatly emphasized. The trademark of a high-pass filter image is that linear filters commonly are defined as bright lines with a dark border. The multi-image manipulation is focused on the spectral ratio, and the ratio image as the technique which used to enhance the results from the division of digital numbers in one spectral band by the corresponding values in another band. The ratio image is the technique which is used for discriminating subtle spectral variations that are masked by the brightness variations. Depends on the particular reflectance characteristic of filter involved and the application at hand. And the ratio image can also be used to generate font color composites by combining 3 monochromatic ratio datasets. The advantage of this technique is combining the data from more than 2 bands and representing the data in color. And now I would like to introduce the way how to calculate the band mark. The band rationing is accomplished by the simple division of one band by another. Band rationing is used to enhance differences between bands which represent spectral filters while suppressing other filters. But sometimes difference in brightness values from identical surface materials are caused by topographic slope or shadows. These conditions may hamper the ability of an interpreter or image classification process to correctly identify surface materials. In many situations, the ratio of digital numbers from a surface with full sunlight, variable illumination, and shading are often very similar. Therefore, the individual bands are often observed to highly correlated or redundant. 2. Mathematical transformation techniques are often used to minimize these spectral redundancies is principal component analysis, PCA, or canonical analysis, CA. The reason why we should apply the principal and canonical component is because the multispectral remote sensing datasets comprise a set of variables, the spectral bands, which are usually correlated to some extent. That is, variations in the digital number in one band may be mirrored by similar variations in another band. When the digital number of a pixel in band 1 is high, it is also high in band 3, for example. In situation, the two techniques will compress all information contained in a n-band dataset into less than n components, or a new bands, scatter diagrams, principal components, and new axes. The solution for principal and canonical component is that principal component analysis (PCA) is used to produce uncorrelated output bands and to determine or reduce the data dimensionality. Principal and canonical component transformations apply either as an enhancement operation prior to the visual interpretation or as pre-processing procedure prior to automatic classification of data. PC bands produce more colorful composed image than spectral color composed image using normal wavelength bands because the variation in data has been maximized. By selecting which PCA bands to exclude in further processing, you can reduce the amount of data you are handling, eliminate noise, and reduce computational requirements. In principal component analysis, the technique computes a set of new transform variables components, with each component largely independent of the others, uncorrelated. The components represent a set of mutually orthogonal and independent axes in n-dimensional space. The first new axis contains the highest percentage of the total variance or scatter in the dataset, and its succeeding lower order axis containing less variance. And the figure is the example for the difference between the PCA and CA. As can be seen in the figure, rotation of X in two-dimensional space for a hypothetical two-band dataset by principal component analysis in the left-hand side and canonical analysis in right-hand side. The PCA used digital number information from the total scenes, whereas the CA used the spectral characteristics of categories defined within the data to increase their separability.